Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today, we're going to talk about matrix representations of linear transformations. First, recall that if you have a vector space V with a basis B consisting of the vectors v1 through vn in an ordered way, and if V is an element of the vector space V, where V is C1 V1 through Cn Vn, then the coordinates of V relative to the basis V are just the coefficients C1 through Cn in a column vector in Rn. For a linear transformation between vector spaces V and W, we need two bases. We need basis for V and we need basis for W. B sub V will be a basis for the vector space V, and B sub W will be a basis for the vector space W. Go figure. Let's suppose that B sub V is V1 through Vn, and B sub W is W1 through Wm. We're not assuming that V and W have the same dimension. Now, let's suppose that V is an element of the vector space V, and so it has coordinates relative to the basis for V of, let's say, C1 through Cn. It makes sense to talk about the coordinates of T of V relative to the basis for W. And in particular, we know that V has a representation as a linear combination of elements of BV with coefficients C1 through Cn. So this is going to be the coordinates of T of C1 V1 through Cn Vn. But due to linearity, we can write this as C1, the coordinates of T V1 relative to the basis for W, plus all the way up to Cn times the coordinates of T of Vn relative to the basis W. But thinking of this as a linear combination of columns of a matrix, the coordinates of T of V1 relative to BW through the coordinates of T of Vn relative to the basis on W times C1 through Cn, but remember this is the coordinates of V relative to the basis on BV. It follows then that if we want the coordinates of T of V relative to the basis on W, one way to get that is to take this matrix consisting of the coordinates of the basis vectors on BV relative to the basis on BW, and then we multiply by this vector C1 through Cn, which are the coordinates of V relative to the basis on BV. So in order to calculate this linear transformation of the vector V coordinate-wise in the range, you take this matrix and multiply it by this vector. We're going to introduce some notation. The representation of the linear transformation T using the basis BV and BW, BV for the domain space, BW for the codomain space, is, by definition, because I said so, the coordinates of T of V1 relative to BW, and all of the columns are just going to be these coordinates of Vn relative to BW, where BV is V1 through Vn. We have, as a theorem then, that the coordinates of T of V relative to BW is the coordinate representation of the transformation T, BV, BW, times the coordinates of V relative to BV. As a quick example, consider the transformation T of xy equals minus yx. What is the matrix representation of? Note that T maps R2 into R2. We'll select BV to be same as BW, which is the standard ordered basis for R2. So the coordinate representation, we'll just call this B, since they're the same. It's the coordinates of T of E1 relative to this basis, and then the coordinates of T of E2 relative to this basis. If we plug in 1, 0, we get 0, 1. If we plug in 0, 1, 0, 1, we'll get negative 1, 0. So the coordinate representation of this linear transformation is as this 2 by 2 matrix. Notice that the coordinates of any vector xy relative to the standard ordered basis in R2 is xy. And then if we try to write T of xy relative to this basis, according to our theorem, we should get 0, negative 1, 1, 0 times the coordinates of that vector xy, which gives you minus yx, and just as you might expect. But who says we have to choose the standard ordered basis? We can choose any basis we want. Let's suppose that the basis on the domain is the standard ordered basis, but the basis on the range is 1, 1, 1, minus 1. Now, what is the matrix representation? We need to calculate T of E1 and its coordinates relative to BW. Well, T of E1, 1, 0, is 0, 1. You can see that if you subtract these, 1 and negative 1, you'll get 0 in the first coordinate and 2 in the second. It follows that 1/2 minus 1/2 are the coordinates of the output, 0, 1, relative to this basis. If I take 1/2 times the first vector and negative 1/2 times the second vector, I get 0, 1. Now, what are the coordinates of T of E2 relative to BW? If I plug in 0, 1, I'll get negative 1, 0. I need to find those coordinates relative to BW. Now, we should have negative 1/2, negative 1/2. I'll have negative 1/2 and negative 1/2 gives me negative 1. Negative 1/2 and negative times negative is positive 1/2, gives me 0. So now, my matrix representation is going to be these two down the columns. What if I'm trying to calculate T of, let's say, 1, 2? I need to calculate that relative to the basis on BW. This should be the matrix representation times the representation of 1, 2 relative to BV, which is itself because BV is the standard ordered basis. So I'll have 1/2, negative 1/2, negative 1/2, negative 1/2 times 1, 2. What is that? It's 1/2 minus 1, that's negative 1/2. Negative 1/2 minus 1 is negative 3/2. But those are the coordinates of T of V relative to B2. What is that relative to B1? Let's remember what these coordinates represent. We get negative 1/2 times 1, 1, minus 3/2 times 1, negative 1. What do you get? Negative 1/2 minus 3/2 is negative 4/2, or negative 2. Negative 1 minus negative 3/2 is 1. Note that T of 1, 2 is negative 2, 1. Right now it may seem like this is all some crazy game with very little point, but let me show you that there is a point. Let's take T, which maps P3 into P2, where T of F is F prime. We know that the derivative is a linear transformation. The question that I have for you is, can we represent the derivative by matrix multiplication? Our theorem says yes. Let's choose the standard order bases for each of these. The basis on P3 will be the standard ordered basis. That's 1x, x squared, and x cubed. The ordered basis that we'll use on P2 will be, of course, the standard ordered basis 1x and x squared. How then do we represent? Let's call this basis 1 and basis 2. How do we represent the derivative as a matrix? First, we take T of 1 and represent it according to basis 2. T of x and represent it by basis 2. And so on. What do we get? The derivative of a constant is 0. The derivative of x is 1. The derivative of x squared is 2x. And the derivative of x cubed is 3x squared. What are the representations in terms of the basis on P2? Well, 0 is no coordinates. 0 for all coordinates. 1 is 1, 0, 0. 2x is 0, 2, 0. 0 times 1 plus 2 times x plus 0 times x squared. And then 3x squared is 0, 0, 3. How can we use this matrix to calculate derivatives? Our formula is T of V BW is T BV BW times the coordinates of V relative to BV. So, how do I then calculate the derivative of A plus BX plus CX squared plus DX cubed? Let's do this in coordinates on the basis for P3. According to our theory, the coordinates of A plus BX plus CX squared plus DX cubed on the basis on P3 is A, B, C, D. We should then be able to calculate the derivative in the following way. We'll take the matrix that we found and multiply it by A, B, C, D. What do we get? we get B, 2C, and then 3D. But these are the coordinates of t of our polynomial relative to the basis on P2. It follows then that t of a plus bx plus cx squared plus dx cubed will have these coordinates for 1, x, and x squared. That's b plus 2cx plus 3d x squared, which you can see by inspection is the derivative of a plus bx plus cx squared plus dx cubed. We now have the ability to calculate derivatives by matrix multiplication. You can see that we are limited here to polynomials. However, who says we have to limit ourselves to polynomials? We'll just have to extend the basis so that we can include a broader array of functions. Our theory seems to only work in finite dimensions, however. As an example, suppose I want to find the matrix representation of a linear transformation where the linear transformation is t of xy equals 2x plus y, x plus 2y, and then just x. You can see that the domain space is R2 and the codomain space is R3. We'll choose as a basis for R2 1, 1, 1, negative 1. And we'll choose as a basis for R3 1, 0, 0, 1, 1, 0, 1, 1, 1. So we need to calculate t of 1, 1. Plugging in 1, 1, we'll have 3, 3, 1. We need to calculate that relative to this second basis. And then when we plug in 1, negative 1, if x is 1 and y is negative 1, we'll have 1, negative 1, 1 relative to B2. How do we calculate the coordinates of 3, 3, 1 relative to B2? Well, we need to know the constants C1 times 1, 0, 0 plus C2 times 1, 1, 0 plus C3 times 1, 1, 1. That gives us 3, 3, 1. In other words, we need to solve the system of equations represented by the augmented array here. We'll find the reduced row echelon form, which is pretty easy to do because if we take negative 1 times the second row and add to the first row, we'll have 1, 0, 0, and then 0. And if we take negative 1 times the third row and add to the second row, we'll get 0, 1, 0, 2. And then the last row stays as it is. So the coordinates that we have so far are 0, 2, 1. Now to calculate the coordinates of the second column. The only thing that changes are the right-hand sides here. So we'll have 1, negative 1, 1. Again, negative 1 times the second row plus the first row gives us a 2. Negative 1 times the row plus the first row gives us a negative 2, and then 1. So we'll have 2, negative 2, 1. On a part B to this problem, I want to use this representation to find t of 2, 3. The first step will be to find the coordinates of 2, 3 relative to the basis on the domain space. Here, we need to solve the system of equations represented by the augmented array 1, 1, 2, 1, negative 1, 3. Negative 1 times the first row plus the second row leaves the first row alone. We'll get a 0 in this spot. Negative 1 times this plus this. Negative 1 times this plus this is negative 2. Negative 1 times this plus this is 1. We'll then multiply through by negative 1/2, and then multiply the second row by negative 1 and add to the first. That'll give us a 0 in this spot, and we'll have 5/2 in the first spot. So these are 5/2, negative 1/2 in coordinates. We then take the matrix representation of the linear transformation and multiply it by the matrix representation of the original vector. We'll have 0, 2, 1, 2, negative 2, 1 times 5/2, negative 1/2. We'll obtain negative 1 followed by 5 plus 1 is 6, and then 5/2 and negative 1/2 is 4/2, or 2. Now these are the coordinates of t of v relative to the basis 2. To figure out what that vector represents, we take negative 1 times the first vector in the basis, 6 times the vector in the second, and 2 times the vector in the third position in the basis. You can see then, if I take negative 1, 0, 0, plus 6 times 1, 1, 0, plus 2 times 1, 1, 1, what do I get? Negative 1 and 6 is 5. We have negative 1 and 6 makes 5, and 2 makes 7. 6 and 2 makes 8, and then 2. Note that t of 2, 3 is 2 times 2 is 4 plus 3 is 7. And then 2 plus 6 is 8. And then 2. Verifying our result. As we've seen, the set of linear transformations from V to W forms its own vector space. If I have T and S that lie in the set of linear transformations from V to W, then their sum will also be a linear transformation. Go figure. And a constant times the linear transformation is a linear transformation. How are the coordinate representations related? Well, the representation of T plus S, basis 1 for the domain space, basis 2 for the codomain space, is just the sum of the coordinate representations. Well, we should be concerned also about constants times linear transformations and their matrix representations. How does multiplying by a constant affect the matrix representation? Well, the answer is it just multiplies the matrix representation by that constant. The proof was pretty simple, so I'll leave it to you. Let's suppose that T maps U to V and S maps V to W. Then S composed with T is well defined, but how are the coordinates related? Let's suppose we have B1, B2, B2, B3. 3 bases for each of the 3 vector spaces. So for the composition, since you end up all the way over at W, you'll use B3 for the vector space out. Well, the matrix representation of the composition is the product of those matrix representations. There's a special notation for linear operators. A linear operator maps a vector space to itself. Let B be a basis for V, then instead of writing T, B, B, instead, we'll just write T with a subscript of B. We have a corollary. A corollary is a theorem that is an immediate consequence of another theorem. Let's suppose that T is a linear operator and T inverse exists. What then is the matrix representation for T inverse? Well, take the matrix representation of T and find its inverse. In our next theorem, we're going to let T be a linear operator. It maps a vector space onto itself. And let B1 and B2 be bases for the vector space V. If P is the transition matrix from B2 to B1, then the coordinate representation of the linear transformation T relative to the basis B2, both in and out, is equal to P inverse times the coordinate representation with respect to B1 times P. Let's see if it really makes sense on the right-hand side. Let's put that coordinate representation for the matrix under B1. P is the transition matrix from B2 to B1. So you're letting stuff in from B2, just like over here, convert to B1, let it act on B1, and then the inverse is the representation from B1 to B2. So back to B2, just like over here. The proof just goes into this in a little more detail. If you have that transition matrix from B1 to B2 times this representation, we said B2, representation on B1, and then the transition matrix B2 to B1, what does that look like in a little more detail? The coordinate representation is T of, let's use V1 V2, Vn, but the whole point of the transition matrix is to convert from one coordinate system to the next. So if we multiply this on the one side, so if we multiply by the transition matrix on the left, we end up with T of V1, V2. But remember, for any vector v, the representation here is going to be the representation of the linear transformation times the representation of the vector. That means that what we had last is going to be T v2 times the representation of v1 relative to b2 through Vn relative to B2, and we're still times the transition matrix from B2 to B1. But if you think about what we have here is the transition matrix from B1 to B2. And that's being multiplied onto the transition matrix from B2 to B1. And these are inverses of each other. And so we finally get the matrix representation of T relative to B2, and that is the end of the proof. And so you see if you have a representation of a matrix of a linear transformation with respect to one basis, it really represents the same thing as the linear transformation relative to another basis. And so these are related in this exact way. This leads to the following definition. Suppose A and B are both elements of the set of n by n matrices. We say that A is similar to B, and write A is similar to B with a little tilde like this if there exists an invertible matrix P such that A is P inverse B P. That's what it means for matrices to be similar. As you can see, different coordinate representations of the same linear operator are similar.